Welcome to 3.5, page 3. We have one problem here, and here's the biggie on this problem. It is not difficult if we read very carefully. However, there are a couple places here where they can kind of trick us, but this is very real-worldy, and they give us a formula to use. The population P in thousands. Man, if I'm reading this, I am pointing that out right now. Our population is given in thousands. If they tell me if P ends up being 12, that's 12,000. Of Pineville, North Carolina from 2006 through 2012 can be modeled by this formula, where our population equals. So what does this 5.4 really mean? It means 5.4 thousand people at the start value. I mean, that's the same formula as what we used back here. It's just y equals a e to the bx, or it's the amount at time t equals the initial amount e to the rt. This is maybe the best generic way to think about it. Same formula right here. Amount at time t equals initial amount, 5.4. E to the k is really the rate of growth times time. Same formula. Watch this, what they're trying to do here, mess with us. Because it's like 2006. Maybe I'd use 0 for 2006, but they say where t is the year with t equals 6 is 2006. And then they say in 2008, the population, so t equals 6 is 2006. In 2008, the population is 7,000. That's in 2008, the population is 7,000. But boy, there's a couple chances for error here. That is t equals 8, because t equals 6 is 2006, so t equals 8 would be 2008. And that is a population value for our formula of just 7. Oh, okay, so the population was 7. It grew from 5.4 e to the k, sorry, down here, e to the k times t 8. Okay, so e to the 8k is 7 on 5.4. If I was to ln both sides, which I'm going to, take the natural log, I get 8k equals, or k equals ln of 7 on 5.4, all of it divided by 8. Meaning my model, find the value of k for the model, round your answer to 4 decimal points. So this is just the value of k. So here we go. Use your model to predict the population in 2018. So I'm going to go ln of 7 divided by 5.4 and then divide that by 8 is 0.0324. Definitely worth noting that's 3.24% that it's growing at. Now, if you've watched the last section, you know I'm really big into using, if you've watched the last few sections, you know I'm really big into using the exact value. This is an approximation. However, since they told us to round it, I'm going to assume for their model they're going to use the rounded value. So our model just became population equals 5.4 e to the k 0.0324 times, I almost put an x there, times t. Use your model to predict the population in 2018. Well, in 2018, if t equals 6 corresponds to 2006, 12 years later, in 2018, 12 years later, t is 12. So this just becomes p equals 5.4 e to the 0.0324 times 12. And we see we did the heavy lifting up here. But where are we apt to make a mistake? This 12. Where are we apt to make a mistake? Still to come. But we're ready to go straight to calculator. You'll see what I'm saying. Still to come. 5.4 Second ln is e to the 0.0324 times 12, and we get p equals 7.96613 dot dot dot. But there's our next error. The population is not that. P is in thousands. So our population really is approximately 7966 people. 1,000, each one of those is 1,000. So not really that difficult. However, you better read it carefully. You better read where it says in thousands, where it says where t equals 6 corresponds to 2006. I would suggest that that would be a problem, that people would know what they're doing mathematically, but just kind of skirt the reading a little bit. So short video, short problem, make certain that you're checking your solution. Again, if we needed some kind of exact value, I would use this ln7 on 5.4 all divided by 8 instead of the 0.0324. But we're approximating.